Hello, I'll be presenting the paper. My name is Wei-Lin, and I'll be presenting the paper evaluating the feasibility of predicting information relevance during sense making with eye gaze data. And the slides are by me. So basically, we're asking, can a computer look at your eyes while you work in augmented reality and figure out what's actually important to you before you even say a word? So to understand the solution, it's important to understand the problem backing this research. As AR tools and VR tools get more popular, we need intelligent analysis aids to help us deal with large amounts of data. The problem is that traditional eye tracking metrics aren't great at the word level because something called frequency bias. Right now, there isn't a solid metric designed for these complex tasks where you're juggling dozens of documents at once. And to understand the solution, we have to look at the struggle itself. So what the sense making basically introduces two problems. First is cognitive load. Sense making makes it's just a fancy word for gathering and organizing and making sense of a massive pile of information. When you're looking at 20 to 30 documents at a time, your brain starts to struggle to track what's relevant. Second, there's frequency bias. If you're just tracking where somebody is looking, common words like the and gets a ton more attention because they naturally appear more. This this effectively masks the actual important details in the documents and that the audience should want to find. So the team research set out to answer these three big questions. How can we design metric based on eye tracking data to capture analysts' focus of the attention during sense making with multiple textual documents? Second question is, to what extent does the metric predict the relevance of documents or words? And third is, how can we use the metric in real-time sense-making tasks to provide intelligent suggestions to the analyst? To solve this, they created a gaze score. It essentially has four components. Gaze duration, this is the total time you're staring at something. The unique dwell, this is how many separate times your eyes jump back to that item. And the z-score is essentially the standard deviation, the statistical deviation from the mean attention level um, of basically how much your attention on one thing differs from your average. And inverse frequency is essentially a weight factor to prioritize more rare words and penalize common terms like the and. For the words, they multiply the z-score by the IDF to generate the gaze score. For their experiment, they used the Microsoft Holo2 lens at 30 FPS and used a dataset of 24 documents to essentially have 12 volunteers do a challenge of reading across documents and then play a detective to deter a terrorist plot. This is the visual of the VR experiment. And for this experiment, they had the procedure such as so. They first calibrated the eyes according to the volunteers to make sure there's a good, accurate tracking. Second, they gave a tutorial for how to use hand-based gestures. Third, they did the 40 minutes task of sense making. And fourth, the subjects basically rated words and documents for relevance, so the team can check if the gaze score was right. And basically, looking at the results, the graph shows the gaze score was relevant content was significantly higher for the junk data. Relevant words scored an average of 2.06, while irrelevant ones were way down at 0.31. Essential documents sat at 0.53, while the distracted documents were in negatives at negative 1.45. The difference was statistically undeniable. The graph shows longitude divergence. Basically, as the session goes on longer, the gap between what you care about and what you don't care about gets wider and wider. And once the analysts finish their initial triage, their first look at everything, their eyes starts telling us a very clear story about what's important. The system had 90% precision for identifying relevant documents, and for words, it was lower at 60%. Why this happened is because the researchers factored that the humans often focused on key terms but didn't consciously realize that they were actually important. So the gaze score actually caught things that the human analysts were missed. So what's next? And this research is super helpful for not just in a laboratory, but design considerations for human-computer interfaces, such as visual attention tags that automatically highlight or change colors if you're ignoring them to prevent missing information. Gaze-based search to have the system suggest search terms based on what you've been looking at the most, and smart clustering to basically surface all the important data to where you can visually see it the best. In short, the gaze score improves that we can use your eyes to predict what matters when synthesizing across data.